Hello, everyone. My name is Ashlynn Stillwell. I am an associate professor at the University of Illinois at Urbana-Champaign, and today I'll be talking a little bit about our work on residential water use. And this is really work that's been led by my recently completed master's student, Gabrielle Besky. So that's why her name is first. This is mostly her work. I just get the honor of presenting it. And so really what we're doing in this work is thinking about what's happening inside the residential environment. And water and energy are both really important aspects of the residential environment. And with those meter level data of water and energy, we can start to understand some of the behaviors of the humans in the home. And those behaviors then help us inform recommendations for conservation and efficiency measures. And so some instances are electricity or natural gas or other energy sources only. And some of those end uses are water only. And some of those end uses are something that requires both water and energy. So things like clothes washers, dishwashers, and especially important in our case with showers. So things that use hot water are particularly important when it comes to resource efficiency in the residential environment. And data is underpinning all of this, and understanding of how we're using resources is an important aspect of that. And so our main motivating question here is, how are water and energy connected at the household level? And so we're trying to better understand what's happening inside the home without invading the privacy of the occupants to monitor their behavior. And so this is very US focused, and we start with the aggregate level data that are available for the residential sector in the United States. And the built environment is this interesting microcosm of water and energy together. And so on the left-hand side here is the residential energy consumption survey that is published approximately every 3 to 5 years by the US Energy Information Administration. And so consequently, these are fairly good data. And what we see is that most of the residential energy consumption in the United States is going to space conditioning in some capacity through heating and air conditioning. But water heating is also an important aspect of that. So water heating is that reddish color at 17% of the total residential energy consumption. So this is including both electricity and natural gas. On the right-hand side is residential water consumption, and these data look like they are more recent because they're from 2016. However, that's only the second time these data have been studied on a quasi-national scale, and these numbers can vary widely across the United States and throughout the world, especially regarding outdoor water use. And so nationwide average in the United States is 64% of our water going outdoors to lawn irrigation, but that number can vary widely from as low as 15% to as high as 90% of total residential water consumption. And so what we wanted to understand was what is really happening inside the home when it comes to water consumption in a specific location, instead of looking at these nationwide averages. And so what we did was quantify, we started this effort by quantifying at the national average level the direct and indirect consumption of water and energy inside the home. And a clothes washer is probably the best way for us to illustrate this, because it uses both water and energy. And so the direct consumption of resources is the electricity for the actual appliance. So that's down here in this gray arrow under direct consumption. There's electricity for the appliance itself, and the appliance uses drinking water for cleaning clothes. And sometimes that drinking water is hot water. And so there's energy required for heating that water, typically either on board the washing machine or in the home. And there's a drain on a washing machine, and that water then goes to wastewater treatment. And so there's both electricity, drinking water, and wastewater that are coming out of this appliance directly, into or out of this appliance directly. But there's indirect consumption associated with each one of those flows. So heating water requires either natural gas or electricity, or in small instances, solar heating. And that water is, the heated water requires additional water for electricity and water for natural gas. Similarly, treating the drinking water that goes into the washing machine requires electricity, and treating the wastewater that comes out of the washing machine requires energy. And so there's these indirect components of consumption and direct components of consumption. And so what we wanted to understand in our initial venture into this was, how efficient could the average household be? And so we phrased this in the context of an abatement curve. And so the vertical axis here is the abatement cost in dollars per kilowatt hour. This first one is for energy itself. And the horizontal axis is the cumulative annual energy savings for the average US home. And each one of these bars represents an efficiency investment that would save energy in the home. And some of them are negative cost, meaning they save money over the lifetime of the appliance, and some of them are positive cost, meaning that upfront investment is never recouped with the savings of energy. And so these wider bars represent more efficiency opportunities, like Energy Star windows, for example, or a bathroom faucet or a shower head. And so this picture is for energy. I know it's very busy and difficult to read, but perhaps the more appropriate one here is for water. And there are much fewer end uses of water inside the residential environment. And an interesting conclusion from this abatement curve approach is that all of these efficiency investments are cost negative, except a dishwasher. And the dishwasher doesn't actually save that much water. A high efficiency dishwasher per US appliance standards doesn't actually save that much water. And so most of our savings here are cost negative, so they save money in the long run, and are saving a fair amount of water. So the cumulative annual water savings is over 35,000 gallons per year. And so these are US national average numbers. What we wanted to start to understand was, how do we make efficiency recommendations for not the average consumer? Everyone is different, and human behavior habits are different. And so we started by collecting our own data through a smart water metering setup. And so we've got 2 years of 1-second resolution data and then some. And we're collecting these at the main entrance to the home. And so we have whole home water use because we are collecting meter level data just downstream of the utilities meter. And with these data, we can start to see different signatures or fingerprints associated with individual end uses. And so here's 3 examples of a shower, toilet, and clothes washer. These are training data, and so they're synthetic in that no one took a 2.5-minute shower in this particular home. We turned on the bathtub, which is this peak here, and then turned the valve such that water was flowing out of the shower head. And it's around 2.5 gallons per minute because that's standards for US shower heads. Similarly, this is 2 toilet flushes that kind of look like a square wave, and the noise is natural because all pipes leak, and the home that we are testing this in was built in 1965. So we would expect some noise in the data. And so with these 1-second resolution data, what we were trying to do was understand, where is water being used in this test home? And how do we understand that without invading the privacy of the occupants? And so we look both at daily, monthly, and event-based data, and some interesting conclusions come out of that. So if we look over 1 year of data, we see that for this particular set of occupants, there's a statistically significant increase in average daily water consumption on the weekends compared to weekdays. And that's to be expected for these occupants that work traditional Monday through Friday, approximately 8 a.m. to 5 p.m. work schedules. And so this is not too surprising, but it is a statistically relevant difference of weekday versus weekend. Then if we look at a typical weekday versus a typical weekend, we also see differences in the diurnal peaks that come with water use. And so residential water consumption typically has a morning peak and an evening peak. And what we see on weekdays, which is here in orange, is an earlier peak in the mornings, no water consumption throughout the day when the occupants are typically not at home, and then a peak in the evening. The blue then shows our weekend average, or a typical weekend day, and the morning peak is delayed by a couple of hours, and there is water consumption throughout the day on the weekends. So this is indicative of things like cleaning, laundry, other water consuming aspects. And one of the challenges that's often been reported in literature is, how do we understand concurrent water use events? And so what we developed was an algorithm to disaggregate water uses from that meter level incoming data and parse out these concurrent water use events. And so in this example, this water use event is classified as a shower with a little bit extra. And so the blue line here is the flow rate, and the orange line is the derivative of the flow rate. And we use those derivatives, or those vector gradients as they're called in the literature, to help us understand when there's a dramatic increase or decrease in water flow, because we're dealing with an incompressible fluid. And so what we see in just looking at the flow rate is a large increase that would be indicative of a bathtub turning on, and then a smaller decrease to a somewhat steady flow rate value, which would suggest a shower. Showers are typically very long duration events, but then during this shower, there's something else that happens and then has this decrease associated with it. And so what this likely is a shower event, and then someone else in the home has flushed a toilet. And we can separate these by looking at the derivatives. So we look for major increases and major decreases, and we match those in an ordering algorithm that sorts them and matches up those major increases and decreases. And then when we notice that there is a major increase followed by a decrease that is not the same magnitude, we look then to consider whether that event is a shower and categorize it accordingly. This is particularly important because, as I mentioned, showers are long duration events, and these particular occupants have young children. And so sometimes those shower events can extend beyond this example that's shown of approximately 17 or so minutes of a shower event. And so we then use k-means clustering based on those disaggregated water use events to start to classify what is happening in these particular end uses. And when we start with k-means clustering here on the left-hand side, we see that showers have kind of their own category because they're among the only long duration events that seem to happen in this test home. These occupants had self-reported that they don't irrigate outdoors very often, and we saw that in their data, that if there was significant lawn irrigation, we would see long duration high flow events, and we really don't see those showing up very often. And so that's consistent with what the occupants are reporting to us in our exploration of their home. And so within our initial clustering set, showers and low flow faucets emerge. And then we have these two categories, the green dots and the blue dots, that we characterize further. And the green dots are what we categorize as washing machine and other, because we do expect to have a certain amount of leaks in this home and a certain amount of outdoor water use, just not extensive outdoor water use. And so we lump all of that together in an other category. Then zooming in on these blue dots, we see clusters of events that start to occur. And one interesting conclusion of all of this is that the devices, the end uses that are not controlled by humans, like toilets, dishwashers, and washing machines, they tend to behave the same way every time, and they tend to cluster very closely together because the occupant is, say, flushing the toilet, and the toilet is behaving the same way every time. And so with this clustering, thanks, Andrea. So with this clustering, we start to then categorize where are these end uses happening. So we have disaggregated concurrent events. We've categorized all of these events over the course of a year, and then we use that to inform a water use estimate for this particular home. And so we present it as a Sankey diagram just to show where the water that comes in the main goes in the home. And these results are very different than the national average. If we took national average values, our efficiency and conservation recommendations would be things like don't water outdoors or use high efficiency irrigation methods outdoors. And for these occupants, that's kind of useless information because they're not using a lot of water outdoors. Our recommendations to them would be maybe taking shorter showers in a conservation effort, or installing lower flow shower heads is the best efficiency recommendation for these particular occupants. And that's because we have used their water use data to inform where water is flowing in their home, and can use that then to inform customized conservation and efficiency recommendations. We also see that some appliances don't necessarily operate as designed and reported by the manufacturer. Some of them do better and some of them do worse. And so our big conclusions from this household level exploration is, of course, there's more work to do, but there's good news in that water and energy efficiency measures have often negative abatement cost, meaning they save money over the life of the appliance or the fixture. And water efficiency is a cost-effective approach to energy efficiency and vice versa. Saving water saves energy, saving energy saves water. And looking specifically at this smart meter rollout that we have on our test home, we can use meter level data to understand where water's flowing in the home and make customized conservation and efficiency recommendations that are not solely relying on infrastructure changes and can also leverage behavior changes. And so with that, big takeaway is, in a data-informed session, really data collection and decision-making are important for both water and energy, regardless of the scale that we're talking about. So I'd like to quickly acknowledge my students that worked on this. The initial nationwide average study was led by Dr. Chris Cheney when he was a PhD student. He's now an assistant professor at the Air Force Institute of Technology. And as I mentioned at the beginning, the smart water metering at the household scale was led by my former student, Gabrielle Bethke, and two undergraduate research assistants, Abby Cohen and Micah Stickling. And so with that, I will take any questions.
Thank you very much, Ashlynn. So virtual round of applause to you too. Any question from the audience? Since we are, let's say, 24 people, that's manageable, feel free also to activate your mic and ask questions in spite of using the chat.
Okay, so can I go, Andrea?
Please.
Thank you, Ashlynn, for the beautiful presentation. I have a few questions regarding the experimental setup and also the experimental data. So first of all, is this a single home that you have monitored, or it is just one?
Right now we're testing one home as a demonstration that we can do it, and we've got additional funding to expand it to new installations.
Okay, and how much does it cost equipment to monitor at 1 second resolution the water flow?
So the metering,
approximately.
approximately the metering setup plus the data acquisition is approximately $400 US.
Mm-hmm. Okay. So, and yeah, okay, thanks. Much less than what it was a few years ago.
That's good news, right?
Yeah, and yeah, have you also calibrated and validated the results? What are the figures here?
So the calibration is difficult because the meter is a customized off-the-shelf meter that we've gotten from a metrology company, and they calibrate the meter on site and then ship it.
No, sorry, there is a misunderstanding. I don't mean the meter. I mean the end uses. So if you have a calibration data set that you use to train the algorithm, and another one to validate, to know what is the accuracy of the algorithm.
We do not. We have a limited amount of training data. And so what we were trying to do in this first study was figure out what could we ask and answer without ground truthing, without submetering in the home, or without asking the occupants to keep a water diary or something that would ground truth those observations. So we have a very limited training set of each one of the end uses in the home with at least 2 observations, but that doesn't necessarily capture things like the washing machine that uses sensing. Depending on how much of a load of clothes is in the washing machine, it will adjust how much water it's using. And so we don't have ground truthed observations to be able to say we have a certain accuracy. We were able to categorize about 90% of the observations, and the remaining 10% got dumped in that other category.
Okay, great.
But that's about the best we can do.
Yeah. I mean, it's a known problem also, Andrea.
Right.
Nola knows it very well because
right.
it was very difficult to get submetering information for electricity is not a problem, full of open data sets, but for
right.
Water, there is basically nothing. Okay, thank you very much, Ashlynn.
Thanks, Ashlynn. Thanks again.